እንዴት ልሰሩት እንደምትችሉ አንዳንድ አይዲያ ሰጣችኋለሁ።
ስለዚህ መቀጠል እንችላለን ማለት ነው።
ኦኬ ጥሩ እሺ። Okay, welcome back everybody. I think you can hear me now, hopefully. So for today, we're going to talk about industrial screening. I probably suggest that you might have gone through some of this content with Dr. Abu Bakr. So I'm not going to talk too much about equipment, but I'll probably focus my discussion mainly on operational factors of screening. And when I say screening, typically I'm talking about screening of minerals, and this screening is related to processing of ores only. So obviously screening can be done for a range of other applications, and you could use a number of equipment for that. So today's discussion is restricted only to screening as applied to mineral processing. Okay, so just keep that in mind when we go through this discussion. But some of this can be transferred and related to other applications. Some of it may not be. Some of it is restricted to mineral processing, but regardless, my focus will be just on aspects related to mineral processing. So we'll talk about briefly just different types of screening, and probably we'll focus more on screening operations and what type of surfaces you use during screening of mineral ores and factors that may potentially affect the performance of a screen. And classification will be a main topic for next week, but this week I'll just briefly touch on some of the theory behind classification, but we'll talk about classification in detail next week. So keep that in mind as well. Okay, so I probably showed you this one before when I talked about crushing and grinding. What I would like to focus on for today is where so my discussion was, for example, a SAG mill ball mill cyclone circuit where you would have a primary crusher, in this case a gyratory crusher, a SAG mill typically used for primary grinding, and a ball mill. But in conjunction with that, as you can see, there is a screen here. Okay, so this screen here is operated in closed circuit with a SAG mill. So any oversize that comes from a SAG mill is recycled back and crushed with a cone crusher in this case. And I told you the reason behind this. The reason is we don't want to send all coarse particles from the SAG mill discharge into a ball mill or into a cyclone directly. We need to control whatever comes from a SAG mill, and that's typically done by putting a screen next to a SAG mill. So I would say my SAG mill is operated at 110 millimeters size, for example, or I could say my SAG mill is operated at 5 millimeters size, whatever the case may be. And the screen here is put to recycle any of the coarse material that is discharged off the SAG mill. And we talked about scuds, for example, which I said were somewhere around 20 to 50 millimeter particle sizes, which don't crush very well in a SAG mill, and they need to be quickly removed and recycled back. Okay, the way we do that is the screen here, and those will be recycled back and crushed. Now the rocks are a bit smaller, the SAG mill can handle them, and therefore we can maximize the efficiency of a typical SAG mill. So that's where typically a screen is applied, on a crushed material or on a SAG mill product. Okay, and I also mentioned to you before, we feed a primary crusher such as a gyratory or a jaw crusher We put grizzlies, which are typically screens as well. Again, the idea behind that is to remove any fine material from going to our primary crusher. If we send fine material to our primary crusher, the impact is that it will choke very quickly and it will reduce the capacity of the crusher significantly. So there's no point in feeding fine material to a primary crusher. So we need to remove that before we feed a primary crusher with large rocks, typically. Okay, so that's where screen can be used in a typical comminution circuit. And of course, the ball mill is operated in closed circuit with, for example, a cyclone. So hydrocyclones are typically used. Again, the main purpose there is split the particles into fine and coarse. The coarse particles are sent back to the mill and crushed and grounded, in this case with a ball mill. The fine particles can be sent to flotation, gravity suppression, whatever the case may be. So again, in this case, the cyclone is used to control particle sizes going into the next step processing. So that's why it's very critical to operate our crushing and grinding in conjunction with a screen or a classifier. So you can't talk really about a complete comminution circuit without paying attention into the screening and classification. And that's why it is important, typically in comminution circuit, and that's why I am discussing about screening today. So to put things into a simple perspective, when we say screening, all we're trying to do is we put a screening surface, we feed coarse material should flow over the screen, fine materials should pass through the screen, and basically we split the feed into fine and coarse. That's just what the basic principle is. There's nothing to it. So the fines will come down here and collected as undersize, and the coarse will make their way all the way over the screen surface and collected as oversize. When do we use screening? Typically, we use it for particles that are larger than 0.5 millimeter. So particles coarser than 500 micron. If your particles are smaller, say, for example, somewhere around 300 micron, 100 micron, and so on, we don't actually use screens because screens are not efficient for fine particles. In that case, we use classifiers. Hence, that's why in that previous circuit that I've shown you, we use classifiers with ball mills because we know particles are fine here. And we use screens either in the case of primary grinding discharge or in the case of a primary crusher feed. Because we know screens work well for coarse particles. At fine particle size, efficiency of screens is very poor because you would need very fine apertures, very fine opening on the screen. And when you're trying to operate the screen at that fine particle size, you blind them very quickly and the efficiency is very poor. So that's why classifiers are preferred when it comes to fine particle sizes. So when do we use in a typical mineral processing operation? It could be that you have very light gangue material and small, dense, valuable material, for example. In that case, you can use a screen to separate one from the other. Okay, so we can use screening to segregate particles into different size fractions, and especially if there's some association between value and waste with size. Sometimes what happens is the gangue deports to very fine sizes or to very coarse particle sizes based on what kind of material you're processing. So in that case, you can put a screen, get rid of the gangue material as quickly as possible. Okay, if you have, for example, clay materials, very fine materials that are essentially waste, you could probably use a screen to somehow upgrade the ore very quickly. Okay, or as I said earlier, you want to recycle material to a crusher. You want to remove fines before you crush. And sometimes when you do grinding, we want to separate coarse from fine and operate, for example, a grinding circuit in closed circuit with a screen and things like that. And there are different types of screens. I think you probably have seen some of these already, so I'm not going to dwell too much on this. But some of the screens that we typically use in mineral processing operations are, for example, grizzlies, which look like these ones, okay, with a bar or metal bar typically. These are usually heavy duty, thick bars that we use to remove fine particles before we feed a primary crusher. And the idea here is that can handle very large rocks, and therefore they can withstand that. They're less resistant to damage and wearing, and therefore they can be used for heavy duty purposes. Sieve bends are also another example of stationary uh, screening, where you feed the material from the top and the screen is somehow bent and material falls on the screen, and the fine particles pass through the screen, the coarse materials flow over the screen. And some screens are actually moving screens. For example, you could have revolving screens like a trommel that I've shown you here in this picture here. So the trommel revolves and you feed it from this end, and this is typically your screen. Coarse particles will be retained in the interior of this trommel. Fine particles will pass through, and therefore fine particles are collected here. Coarse particles eventually pass through the screen and collected here. So you have a coarse and fine portions. And you can have shaking, gyratory, vibrating, reciprocating, a number of different types of motions applied to a screen. And typically that's used to improve the screening performances. So as I said, I'm not going to talk too much about equipment specifically to screening, but if you guys want information about different type of screens, I can also happily provide you with resources. But I think this is probably covered in another unit. So what I will probably focus a bit is on different types of screening surfaces that we use in mineral processing operations. Maybe you know some of them. Okay, some screen surfaces are made from woven wires. Some screen surfaces are made from rubbers and polyurethane. Some screening surfaces are made from metal bars, as I showed you earlier. And even some can be made from a metal plate where you can just punch holes on the surface of that metal. You can, for example, punch circular holes or rectangular holes on a piece of metal, and that can be used as a screen as well. So we'll talk about some of this in the next slides. So punctured or perforated screen surfaces, as you can see here. So this can be, for example, a stainless steel plate. And on this stainless steel plate, you basically make holes. And these holes can be of different sizes depending on your screening requirement. This can be large or small. Okay, if I'm screening fine particles, obviously I'll make this finer or smaller. If I'm screening coarser particles, I'll make the holes larger. So depending on whatever is happening, you can punch holes of different sizes on the surface, and that can be used as a screen surface. So basically, whatever screen you are using, whatever motion you apply to the screen, everything else remains the same, but the holes that are punched can be of any shape. They can be circular, rectangular, and so on, as you can see in these pictures here. If you have something like this for screening surface, they're heavy duty, they resist wearing, but the downside is that they probably are not higher in capacity, simply because, as you can see here, there's a lot of area here where you don't have openings on. Usually screen capacity is related to the open area available on the screen surface. So when you make holes, usually you will have open areas, but also there's a large fraction of area that's not available for screening. And therefore, usually punched or perforated plates have a lower capacity as compared to, for example, woven wire screen surfaces. But again, the plate itself can be stainless steel or can be rubber, can be any other material. Again, the rod deck screen, probably as you can see in this image here, you basically line rods in parallel to each other, and you feed material from this end. As the material usually goes down under the influence of gravity, fine particles will pass through and coarse particles will make their way here. And that's how we separate them from one another. And again, this is a very common screening surface, especially as I mentioned earlier, when you're dealing with very large rock. Okay, heavy duty operations can be performed using road decks. And sometimes if you have lots of clays, they tend to be very sticky, and that means the screening operation is affected significantly because clays blind the screen surface very quickly. If that's the problem you have, then road deck screen is very good as they have resistance to blinding and so on. And they can be used again for different type of operations, typically where blinding is a challenge. Wedge wire. So the name wedge simply comes from the shape of the surface. So when you look at the screen surface itself, probably this picture here shows what is going on under the screen surface. So there is a wedge-shaped wire that's making up this kind of screens. So the opening is small, very close to where the screening is happening. But once particles pass through that little gap there, it is free to fall through, which means blinding can be significantly minimized if you use a wedge-shaped surface like this one here. Okay, so wedge shape reduces the blockage or the blinding, and of course you can make them into rectangular, cylindrical, or whatever. But the main advantage of these ones is that once small particles pass through that little gap there, they can fall through easily, and therefore they can be operated at a reasonable efficiency. Woven wire, probably this is more common in many places. And again, we just use a steel, which is drawn into a wire, and then we wove the screen surface using those wires. So this picture here probably shows you what is actually going on. So basically, the wires are woven in a mesh-like structure, and screening surface is simply based on that open area available between the mesh. And again, this can be, of course, woven in different sizes. You can make the hole larger or smaller, and you can make the wire thicker or thinner. So the difference is obviously when you make the wire thicker, you are reducing the open area available for screening. But on the other hand, you actually increase the durability of the screen. So if I'm dealing with very abrasive particles or very large particles in my operation, I tend to make the wire thicker. If I'm dealing with finer particles and capacity is my main target, then I can make the wire thinner, increase the open area, and therefore that will help the screening performance significantly. Okay, so these are some of the things we can do to improve screening operations. Obviously, the wire can be in a square or in rectangular shape, and usually when you have square mesh, is well suited for coarse screening, and rectangular mesh is suited for finer screening. These are probably some of the emerging screening surfaces that the polyurethane. I've seen newer screening machines these days when I go to mining sites. I see some of these becoming more common, more prominent, and most of the screening equipment these days are actually they use surfaces that are made from polyurethane. So there are a couple of advantages. So the polyurethane surface, for example, when you compare it to rubber, they're a bit elastic, which means they don't blind quickly. So this is one of the advantages of a screening surface. Because we know screening surface is significantly impacted by blinding or blockage, basically, of particles. When you have blockage, your screening performance reduces very significantly. So you don't want that. So if it's something made from elastic material, once particles peg or goes through the screen, if they block, because the plastic is a bit elastic, it actually allows for the particles to pass through. And therefore, that can be a good advantage compared to, say, something that's made from metals or something that's made from rubbers, and therefore these days I think modern screens are tending to use polyurethane as a screening surface. And also compared to rubber, for example, the opening cast can be accurately cut, which means you have a precise screening happening on the surface as well. And of course, the polyurethane is a lot more resistant to wearing and so on. So if you have abrasive material, again, they could be a lot more advantageous compared to any other screen. Of course, there are lower noise levels associated with them as well. So there are some advantages in using this kind of material for screening. Okay, so again, I'm going to focus, as I said, on operational factors, but I think before I proceed, if you guys have any questions, feel free to ask now. Any questions on what I've said so far? Okay, if no questions. So one of the issues when we do screening, as I said, is that if you don't operate your screen correctly, usually they blow quickly and the operation or the efficiency of a screen drops significantly. And that is usually an issue. And people have been trying to somehow find a way of measuring screen efficiency. Obviously, when you try to maximize efficiency, the capacity of your screening operation may suffer. Okay, so we want to screen a lot of material, but at the same time, if we want it to be efficient, those two actually don't go together. So when you increase capacity, usually efficiency decreases. Okay, or when you reduce your capacity for the same screen, the efficiency usually is higher. So those are obviously competing requirements, but in any case, for any given screening capacity, we want to also improve the efficiency. So when I say capacity, it's just amount of material we screen in a given time on a given surface. Okay, but when you say efficiency, it is that there are fine particles in the feed to the screen. Efficiency simply tells you of the fine materials, what fraction actually went to the fine fraction. If I started with, for example, 60% fine material in the feed, 100% efficient screen will give you all the 60% fine material going to the fine fraction, essentially passing through the screen. But typically that's not realistic. We don't get 100% efficiency in a screening operation, but we can measure it relative to that. So I have 60% fine to start with in the feed. How much of it was actually recovered in the fine portion? If it is 50% of that, then so your screening is maybe reasonable. If only half of the fine went to the fine fraction, maybe it's not efficient. So we can always track the initial fine material we have on the feed or in the feed to what we have collected in the undersized material, and we can work out the performance of a screen after that. And we'll talk about how we can measure screening efficiency. So maybe, as I said, one example would be I have 1 ton of material to screen. I take a sample from that and I do my particle size distribution analysis. Maybe this is using sieves, as we mentioned last time. And I roughly work out the particle size distribution of the feed material. So I know exactly from my 1 ton that is available for screening, take maybe a few kilograms of the sample, do particle size distribution, you know how particles are distributed. So if I wanted to measure screening efficiency, I can then say, now, if I took, let's say, of the 1 ton, if I took 100 kilos, in that 100 kilo, I can work out the proportion of fine material and proportion of coarse material. So when I say fine and coarse material, maybe my separation size in this case could be, for example, let's say 10 millimeter size. So I can say, I know this much is coarser than 10 millimeter, and this much is finer than 10 millimeter in my feed. Okay. This is done, as I said, through particle size distribution analysis. Then, to measure efficiency of a screening performance, you can, for example, use this formula here where you say efficiency for undersized product can be obtained by simply working out mass percent of feed reporting to the undersize. So now after screening, how much of it is less than 10 millimeters, okay, in the fine portion. I can work that out again by doing particle size distribution. And as I said already, I know the mass fraction of the undersize in the feed because again, I did initially particle size distribution. So basically what you're saying is already in the feed, I had this much undersized material. I did my screening. I took a sample from the undersized portion, which is now coarse and fine. So I'm talking about the fine. And I can measure what fraction of that was actually related to the initial fraction of the undersized that I have in the feed. So if your screening operation was 100% efficient, what you're saying there is I started with this much fraction of undersized in the feed. If all of them passed through the screen, then your screening is 100% efficient. But in reality, some of the undersized will go with the oversized material because you probably have blocked the screen. Instead of passing through the screen, some fine material will still report with the oversize. So you can't collect 100% of the fine material in the undersized fraction. So that's why we can just track undersize in the product and undersize in the feed, and we can work out the percentage and determine the efficiency. And not only the undersize, you can also track the oversize. Again, I have this much amount oversize in the feed. Now I've performed my screening operation. I took sample from the coarse fraction after screening, and then I can then work out that, okay, and then determine screening efficiency. Obviously, for the oversize, if the screen is damaged, for example, some coarse particles may fall through the screen. And again, that may reduce the efficiency of your screen. Typically, when we do screening, we track the undersize, okay, because people tend to assume that oversizes shouldn't pass through the screen anyway. So if we track the undersize in the feed and the undersize in the fine portion, we can work out screening performance. Okay, but as I said, you can also track the oversize as well as the undersize. Okay, another way of determining efficiency of screen is using a mass balance operation. So again, if you remember last time, we can use mass balancing to track flow of water in the circuit, to track solids flow in the circuit. We can try to follow maybe a particular component. For example, if it's a copper plant, we can just follow the copper in the circuit, where copper is going from where to where. We can even track particle sizes from, say, feed to the crusher to whatever comes out of the crusher and so on. And we can follow the same thing for a screening operation as well. So for example, if you say, I start with a given mass of feed going into a screen, I do my screening operation, I collect overflow, oversize and undersize. Okay, so I can then weigh them. So weigh the oversize and the undersize and the feed. If you did that, you have F as mass of the feed, C as mass of the coarse material, and U as mass of the undersized material. So basically you split material into two, fine and coarse, right? But in each of those, in the feed, I can track the fraction of oversized material. So when I say oversized, if my screen here, the opening here was 50 millimeter, so that will be my separation size. So I will say in the feed, this fraction was coarser than 50 millimeter. So that's why we can say coarse material in the feed here is represented by small f. And of course, you're going to have coarse material in the coarse fraction. So what is a coarse material in the coarse fraction? And what is the fraction of coarse material in the undersize? So when I say coarse, particles that are maybe 55 millimeter in size, may pass through a 50 millimeter screen. Why? If there are some damages on the screen. Okay, so we can determine those as well. So there, now you have masses for feed, coarse, and fine. You also have component balance only for the oversized material. So when I say oversized, oversized fraction in the feed, oversized fraction in the coarse, oversized in the underflow, which are represented by small f, small c, and a small u. If I did that, obviously for overall mass balance, the feed is split into coarse and fine. So in this case, nothing is actually accumulating in the screen. You shouldn't expect anything accumulating in the screen. So whatever you feed the screen either goes to the coarse or the fine. Okay, so that's what this one means. But also I can follow where the oversize is going. I have oversize in the feed. This oversize in the feed is split into oversize in the coarse and oversize in the fine. If you did that, then you have what we call mass balances from overall mass flow and component flow. And you can have these equations here, which then can be used to work out screening performances as shown in this slide here. Okay, so using these two equations and rearranging and using that definition of screening efficiency. For example, if you wanted to work out recovery of oversized material into the oversized portion or screen overflow, you can get this equation here. If you are interested in recovery of the undersized material going into the underflow, you can use this expression here. Okay, either way, you can use component and overall mass balance to work out screening efficiency as well. Okay, so as you can see here, the use of accurate particle size distribution is very critical because we're basically relying on particle size distribution of the feed, particle size distribution of the coarse portion, and particle size distribution of the fine portion. So this is one way of doing this. And again, when next semester, probably when we talk about separation, mineral processing techniques, recovery and grade are very critical. Okay, so again, we use exactly the same formula to work out recovery of minerals or working out the grade of a concentrate, for example, after a separation operation. So these are common mathematical formulas we use for those kind of scenarios. So again, overall efficiency, so the combination of recovery of oversize and recovery of undersize can be done using this equation here. And if you look here, so again, you can assume here, if I say here, actually, my screen is very intact. There is no breakage or there is no deformation on the screen surface. We're basically saying oversizes shouldn't go here. If particles are coarser than, as I said earlier, 50 millimeters, they shouldn't come here. So you can say actually the U here can be taken as 0. No oversizes in the fine portion. If that's the case, you can simplify this equation into this one here. And you say efficiency is dependent on coarse fraction in this case, coarse particles, which are above 50 millimeter in my example, in the coarse component after screening. And these are coarse particles in the feed, divided by 1 minus the fraction of coarse in the feed, multiplied by the fraction of coarse particles in my overflow after a screening operation. Okay, so this can be one way to work out a screening efficiency. Probably the most common screening efficiency formula we use is the so-called Trombe curve or partition curve. Because in this case, what we are assuming in these two examples I've shown you is you feed everything to the screen and you're assuming particles. For example, as I said, if this was 50 millimeter aperture size, I'm assuming if a particle is 49 millimeter in size, it should pass through that screen. But in reality, unless you present that particle in a perfect way, a 49 millimeter particle doesn't pass through a 50 millimeter screen. Why? Because it's very close in size to a 50 millimeter screen, and it simply bounces off and reports to the oversize. Even particles that are, say, 55 or 45 millimeter in size, for example, 45 millimeter particles will be very difficult to pass through a 50 millimeter aperture. Why? Because it's very close in size and you have to present it perfectly, maybe with your hand. It will pass through if that's the case. But on a screen surface, because particles are randomly presented, chances are a 45 millimeter particle is not going to pass through a 50 millimeter aperture. Although the aperture is larger, the hole is larger than the particle, because the particle is very close in size, it's not going to pass through. So this assumption of screening efficiency calculation simply relies on the fact that every particle smaller than the screen size should pass through, which probably is not the case in reality. So what the Trombe curve or the partition curve account is for that. So they assume there is the reality that if particles are very close in size to the screening size itself or the aperture size, chances are they're not going to pass through. So we need to account for that one. Okay. And what it says is the partition coefficient can be obtained by working out the fraction of any given size in the oversize to the fraction of any given size in the feet multiplied by 100. Okay, maybe this statement may be too confusing. So what I will do is maybe go to the next figure and show you what I mean. Okay, so let's say you have particles that are anywhere from 1 millimeter to 1,000 millimeter, or maybe even 2,000 millimeter in this case. Okay, so assume particles from 1 millimeter to 2,000 millimeter in size, distributed all over my sample. Okay, so in this case, let's say you choose a screen of about 200 millimeter in size. So your assumption will be particles that are smaller than 200 millimeter will pass through this screen. Particles that are coarser than 200 millimeter will simply flow over the screen and report to the coarse fraction. So in this case, what we know from reality is if particles are, for example, very close to the 200, let's say 180 millimeter, those 180 millimeter particles have hard time passing through the 200 millimeter opening. Okay, that is because usually particles cannot be presented perfectly. Some will pass, of course, but some are not going to pass. So then what the Trombe curve tells you is for any given size, okay, so Wi is any given size. We come here on the x-axis and we say, for example, a given size, say, in this case, somewhere around 250. Although you expect all the 250 millimeter particles to report to coarse fraction, what this one is saying is actually only about 65% report to the coarse fraction. Okay, and the same is true here. For example, if I take particles that are about 100 millimeter in size, okay, and my screen is 200 millimeter in size. So here it says, although particles are only 100 millimeter in size, okay, about 20% of them actually are not reporting to the fine proportion, but they're reporting to the coarse proportion. Okay, so in this case, about 20% of the particles, which are about 100 millimeter in size, instead of going all to the fine fraction, 20% of them report to the coarse fraction. So this partition coefficient was built by taking any given particle size and working out the proportion of them going into the coarse fraction and the proportion of them going into the fine fraction. So ideally, what I would expect is this is my separation size. So this is my screen size, about 200 millimeter. All particles that are coarser than 200 millimeter, 100% of them will go to the coarse fraction. So this is the line I would expect. And any particle that is smaller than 200 millimeter, all of them should go into the fine proportion. So the fraction in the coarse is 0 because all of them went to the fine proportion. So the coefficient here is only for proportions that went into the coarse fraction, or in this case, the oversize. So that's what the oversize here stands for. So it simply tells you for any given size, what fraction went to the oversize. Okay, so for any given size on the x-axis, it tells you what fraction went to the oversize. Okay, so naturally we'll expect the fines to go to the fine proportion. So we expect 0 to go to the oversized portion. And the coarse particles, we expect most of them, obviously, to go to the coarse fraction. But in reality, this curve here is what we get. Okay, instead of getting a perfect Z or a perfect S-looking curve, in reality, we get this curve here because we know screening performance is not 100%. Some particles which should have gone to the coarse fraction will go to the fine, and some fractions which should have gone to the fine will go to the coarse. But in reality, usually the fines are the ones which determine efficiency because we expect all the fines to go to the fine portion and all the coarse to go to the coarse portion. But what happens in reality is some of the fines will report to the coarse fraction. So if too many of the fines report to the coarse fraction, then your screening is very poor. And that's why we can use this curve. So again, the more this curve is close to this perfect separation here, the more efficient your screening performance is. If this curve is very far from the ideal separation curve, for example, if I get something like this one, if you can follow this arrow here. So if it looked, for example, something like this one, then I know the screening performance is very poor. So what I'm telling you is, if you give me, I don't know what you did with the screening operation. If you gave me, this is the screening I have done, this is the feed, this is the product, and this is sample from the fine and coarse, I will just construct a partition curve, and I can tell you that the screening operation was good or a screening performance is bad, just based on what the curve is showing. Okay. Okay, I'm not sure how much of you were following. Again, maybe this can be slightly complicated, but I will do an example on this particular issue next week on a simulated data. So hopefully that will make things a bit clearer as we go. Okay, so don't stress too much if you're not really following what I'm talking about. At least what I want you to to understand is that there are a few ways of working out screening efficiency, and the Trombe curve or the partition curve tends to be one of the better ones. Okay. So how do you calculate screening efficiency? You can use imperfection, which is actually determined using this equation here, D75 minus D25 divided by 2 times D50. So what are D75, 25, and so on? So your D50 here is the size where the screening is being performed. So when I say this, if I say, okay, my screen has an aperture size of 100 millimeters. Okay, so that will be my screening size. So basically 100 millimeter is my screening size. Smaller particles than 100 will pass through. Coarser particles than 100 will overflow and collected as a coarse portion. Okay, so how about if I have particles that are exactly 100 micron or 100 millimeter? I think I was saying 100 millimeters. So if particles are 100 millimeter in size, what this theory is saying is they have equal chance to go to either the coarse fraction or the fine fraction. Okay, so that's why 100 millimeter is my separation size. Okay, so in this case, D50 will be 100, or I think in this example, it is 200. So 200 is my screening size. So particles at 200 millimeter size, they can go either way. So their partition is 50-50. So that's why this is 50% or 0.5 fraction. Okay, particles that are coarser have a higher chance of going into the coarse fraction. Okay, so the D75 here tells you a size, a particular size at which 75% of them go to the coarse portion and 25% of them go to the fine portion. Again, from the curve, you can work out that size. The D25 tells you a particular size of particles which 25% of them report to the coarse fraction, and obviously 75% of them report to the fine proportion. And of course, you can again determine that from a curve. So once you determine those three sizes, then you can calculate imperfection. Okay, so obviously, if imperfection is close to 0, tells you a highly efficient screen. If imperfection is close to 1, it tells you a poorly performing screen. Okay, so it's just a ratio that you can take. Okay. Any questions, guys? Does that make sense, whatever I was talking about? Any questions?
Okay. Have you heard me?
Yes, I can hear you.
What are the factors increasing or decreasing the efficiency of the screening?
Yep. Very good. So I think we're going to talk a little bit about those factors in the next slides. But in what I have discussed so far, the main factor would be the proportion of particles that are close to the separation size. Okay, so for example, if you say my screen aperture is 100 microns, you need to know the proportion of particles that are very close to that size. If, for example, the majority of the particles are somewhere around 90 micron, 95, 105 micron, and so on, those particles are very close to the screen aperture size, which means it is very difficult for those particles to pass through the screen. So the screening performance will drop very significantly. So you need to work that out and determine exactly the proportion of particles near the aperture size. But of course, there are a number of other operational factors. What is the open area, for example? Okay, and so on. So we'll talk about some of this in the next slides. Okay, and any other question?
Yes.
My question is on the screen efficiency.
Yep.
When you deal about screening,
Yep.
it's separate based on size.
Yep.
But mostly there are different types of screens.
Yep.
Some screens may be effective on separating a larger quantity of materials,
Yep.
and some may be effective in separating high grade quality materials. So,
Yep.
in what way will you consider the effect of the screen based on its quality that we will get from the final product, or based on the amount of material that will be screened out? Based on what we will.
Yeah. So yeah, I think that's a very good point. So eventually, whether you look it from any angle, when we say screening or efficiency of screening, it is based on size. Okay, so it is based on the sizes and splitting them into fine and coarse. Okay, so that's what we're looking at when we're looking at screening. In terms of how do you operate it, you can operate it in different ways based on the nature of what you're trying to obviously screen. So if I have sticky particles, which are difficult to pass through the screen, I operate it differently compared to particles that are segregated from one another and easily to flow on the screen surface. Okay. But eventually, if I'm also prioritizing, as you say, amount of material processed, then if the quality doesn't really matter. For example, if I say, oh, I just roughly want to split this into two portions, fine and coarse, and I want to process as much material as possible, obviously, in that case, it is only the capacity that matters to you. If that's the case, then you can, for example, overload your screen, you can move the screen fast, you can do things to actually maximize efficiency, capacity. But in some cases, it is not just about how much material you process, it's actually the quality of products you produce. For example, I could be very strict and say, okay, I want to separate in as much possible the fine from the coarse. And in this case, maybe I'm just trying to control my grinding performance. So I'm not allowing any coarse particles to go to the fines and any fines to go to the coarse, because otherwise, if I allow, for example, fine particles to go to the coarse, I know I'm going to grind them. I'm going to end up over grinding them. It's going to cost me money. So in that case, I'm actually more worried about the quality of the product rather than the capacity. So if that's the case, then you need to reduce the capacity. You need to try to maximize the efficiency of the screen. So I think it depends on what you are trying to achieve. And obviously that's dependent on the consequence of that. So as I say, if quality is what you are after, then capacity should be reduced. The amount of material processed should be reduced. Okay. But probably some of the questions may be answered in what I'm going to talk about in these subsequent slides anyway. We can operate a screen differently to maximize efficiency and so on. And that depends on a number of factors. So I'll probably talk about those ones. Okay, so this part here is mainly focusing on how you operate a screen. Can give you either highly efficient product, highly efficient screening operation, or you can actually operate them slightly differently to maximize the capacity. And some of the considerations during screening operation are given here. So I'll talk about each of these. Okay, so the first factor that can be very critical in operating a screen is relative size of the particle to that of the aperture. So when I say this, so if this was my screen size, okay, so I know the average size of the opening here. Okay, so that is fixed. Even if there was slight differences between the openings, I know the average size is fixed. So what I want to know is what are the fraction of particles that are very close in size to my screening aperture. Okay, if that's too much, if there's a large fraction of particles very close in size with aperture size, then screening is difficult. How do we know that? We know that, for example, by using these empirical models given here. So in this case, screening efficiency can be related to probability of passage of particles, and that is dependent on the open area available for the particles to pass. This is the one I just showed you earlier, the open on the screen, the open area on the screen, divided by the total area on which the particles fall. This is simply the area of the whole screen. Okay, so if I give you a plate that's 1 meter by 1 meter, and as I said, maybe you have punched holes on that plate, maybe 20% is open area. The remaining 80% is still closed. Okay, so the area available for screening is that 20 area, the open area. And the whole area would be the 1 by 1 meter I have just mentioned. So obviously, if the open area is larger, so for example, if it is 60% open area on the surface, the probability of passage is going to increase significantly because probability of passage depends on open area available. Okay, so in this case, if it's say a woven wire, probability of passage will depend on the diameter of the aperture, which is the area of the opening, okay, how big or how small the holes are, and the size of the particles that are falling on it. So this is the DO, okay? And of course, if it's made from wire, it is the wire diameter, which is given by DW here. So in this case, probability of passage will be higher if the diameter of the aperture is higher, which means if the open area is higher. Probability of passage will be reduced if the diameter of the wire is increased. For example, if the wire that used to make the screen are thicker, what you're doing is you're reducing the open area significantly. And therefore your probability of passage should decrease. Okay. So obviously, as the particles get smaller and smaller, your probability of passage should also increase significantly for a given aperture size. So whether you look at it from any angle, usually what matters most is the size of the particles, of course, the open area and the diameter of the aperture, and the diameter of the wire, or how thick the material is, if it's a wire, woven wire, how thick the wire itself is. Again, we're assuming, again, this is the fact that where spherically shaped particles are presented to the screen, they fall in one go. We're not even allowing particles to be presented many times to the screen. We're not even considering a lot of factors here. But we also know, in addition to these factors here, if I move the screen, if I lift particles up and down, I am actually giving them opportunity to be presented in different orientations on the screen, and I'm increasing the passage of particles on the screen. Okay, so there are a number of other factors in addition to just the diameter of the aperture and the diameter of the particles. But if we're just focusing on particle size and aperture size, I'll just talk about this table here. Okay, so as I was saying earlier, if particle size is very close to aperture size, probability of passage is reduced significantly. And that was actually shown in a study many, many years ago, where, for example, in this case, particle diameter was compared relative to aperture diameter. When I say here in this table, this ratio is 1, it means the particle is the same size as the aperture diameter. Okay, so in this case, if the particle is the same size as the opening, that particle shouldn't pass through the screen. And therefore, probability of passage will be 0, as you can see here. Whether I present whether I try maybe 10 attempts or 1,000 attempts, probability of passage will be 0 because that particle is the same size as the aperture, it can't pass through. Okay, very simple. How about if my particle is very small compared to the opening? So when I say very small, so how about this ratio is, for example, 0.1. So what I'm saying here is the aperture diameter is 10 times larger than the particle diameter. Or basically you can fit 10 particles in that aperture. Okay, in that one aperture, 10 particles can be fitted. Okay. If that's the case, if the diameter of the particles is really, really small compared to the diameter of the aperture, that particle should have no problem passing through. Whether the wire diameter is the same as the aperture diameter or not, okay, the particles should pass through with relative ease. Whether I'm presenting it 10 times to the screen or I give it 1,000 attempts, that particle should pass through. Why? Because relatively, the particle is very small in size compared to the aperture size. Okay. How about if it is somewhere around half of the aperture size? If particle is half of the aperture size, so in this case, maybe the aperture is 100 micron in size, but the particle is 50 micron in size. Okay, half of the aperture size, or maybe you can fit 2 particles in one aperture. If that's the case, then screening or probability of passage will be reduced. But if I present that particle many times, if I give it a lot of opportunity, that particle will eventually pass. So in this case, if I say 1,000 attempts, the particle will pass through. So when I say 1,000 attempts, for example, if you use a sieve, in a sieve, we put particles in a sieve and we give it a shaking motion. Okay, so the sieve is shaked. Basically, what we're doing in that case is we're giving the particle opportunity to be presented many times to the screen, and hopefully one of them will give you the chance to pass through. Okay, so going a bit down. So in this case here, somewhere around 0.9, we're actually saying the size of the particle is very close to the aperture size. So in this case, almost 90% of the aperture size. Maybe you're looking at if your particle was, if the aperture was 100 micron, the particle was maybe 95 micron in size. Okay, something like that, or closer. So in that case, what happens is the probability of passage reduces significantly. So for this close size particle to pass, you need to present it many times. You need to give it longer screening time maybe, or you need to increase the shaking motion and so on, so that that particle is presented many times. And hopefully, again, you give it opportunity to pass through. So what we're saying here is screening performance is significantly affected by how close the size of the particle is compared to that of the aperture size. So then in a real operation, what do we need to do? So in a real operation, you need to do proper particle size distribution analysis of the feed. You need to determine the particle size distribution, and you need to know where most of the particles are aggregated at. So you can work out the size. If the majority of the particles are close to one size, then you shouldn't pick a screen around that size. Your screen should be higher than that size or very smaller than that size. Otherwise, if the screen size is close to a lot of particles, closest to that size, then efficiency will drop significantly. Okay, so this is one way of measuring or factors that affect the performance of a screen. Obviously, another factor, as I said, is how much open area you have. Okay, so if you reduce the wire diameter, as I said here, if I reduce the wire diameter, automatically what I'm doing is increase open area. Okay, open area available will depend on the wire diameter. Thicker wires mean you're blocking more of the open area here. Thinner wire, you're giving it more open area for screening to happen. So that's why we say here, decrease in wire diameter will lead to more open area, and that more open area should help the screening, should increase capacity, should increase efficiency. Okay. So where are the times when you can make the screening surface from thick wires? That's when I'm dealing with very large rocks, when I'm dealing with abrasive rocks, okay? When particles are falling from a height, they can easily damage the screen, okay? So again, if that's the case, then I need to make the wire from thicker wires. I need to make the screen from thicker wires, and those are the cases where that can be applied. Okay, shape of the opening on the screen can be any shape, can be rectangular, can be square, can be circular. So that depends again on what I want to do. If my particles are elongated, very irregular shaped, maybe for elongated particles, rectangular screens are good. If I want to do very accurate sizing, okay, then I will use circular openings, and that will be what I would want the screen surface to be made from. So again, depending on the operation, you can choose different aperture shape, and those will serve different purposes. But of course, you need to be aware of the limitations of each of these ones. For example, if you have circular apertures, that will mean you have a small fraction of open area, and the capacity reduces significantly. So either you need to increase the area of the screen itself, okay, or you need to run it quickly to compensate for capacity. But in any case, you need to consider the pros and the cons of different screen shapes. Again, how do I orient them? If I have, for example, rectangular shaped openings, you can use it, as I said, for elongated particles because it gives you a larger efficiency. If screening was done this way, then I also increase the capacity of, for example, a rectangular screen. Okay, these are some of the minor things you can do to adjust for increased capacity and so on. If, as I said, I want some balance between, say, efficiency and capacity, maybe you can put, for example, rectangular openings or slots can be made perpendicular to the screening direction to maximize efficiency as well. So I mentioned about diameter earlier. The main issue with wire diameter is open area. More open area for thinner wires, less open area for thicker wires. Obviously, thicker wires will have lower capacity. Another factor is length and width of a screen. Okay, so you can make the screen itself either very wide, the equipment can be made very wide, or it can be made long. But this is just what is the impact of, for example, a long screen. If I say long screen, then I'm giving particles good opportunity for them to pass through this screen. So when I say length, if this is really long, particles spend more time on the screen surface, so my efficiency improves significantly. But on the downside, of course, capacity decreases. Okay, so that's one of the impacts of having longer screen. The width obviously increases capacity, but usually doesn't have much effect on the efficiency of a screen. Angle of inclination, as I showed you earlier, for example, grizzlies are inclined, and that is usually used to help particles fall under the influence of gravity. So that actually helps with transport of particles from the feed end to the product end. And if you incline it too much, particles pass through very quickly. Maybe you reduce efficiency, but you improve, of course, capacity of them. And inclination also helps with particle segregation and stratification, which can be also beneficial to improve efficiency. Again, I mentioned about screen movement. So what's the main purpose of screen movement? It's all to do with presenting particles in many positions, giving it chance to pass through the screen. So it's basically lifting it up and down on the screen. And as you do that, you can do quick frequency up and down motions, or you can actually make it longer. So you actually lift particles higher on the air and they fall back. So you can do either faster or longer strokes. Either way, you are helping particles to pass through the screen, and therefore that can increase efficiency significantly. So usually most screens that you see, they have either vibration motion or rotational motion, some kind of motion applied to the screen surface, and that's mainly to do with helping with screen efficiency, owing to the fact that real transport is increased. Okay, so when I say, for example, stratification, when you feed the screen, the coarse particles, fine particles, everything is in one pile. As you move the screen, as you shake it, for example, fine particles will make their way down to the screen surface and they pass through. So movement helps with stratification, and stratification obviously helps with higher or better efficiency of screening. So this is just how, for example, a movement can assist in particles like this one. If you don't move it, it will just simply go to the oversize. But if you lift this particle up and down, eventually, maybe you present it nicely and it can easily pass through the screen surface. Okay, depth of bed. This is how you load the screen. So obviously, you can give it too much material and overload the screen, or you can feed it in a very thin layer. So either way, you can talk about different consequences of that. Maybe I'll talk about this in this one here. So obviously, if this was your screen, at the feed end, you have fine material, coarse material, everything is clogged together. Okay. So what happens is, unless you apply some motion or unless particles make their way down on the screen, here screening is very poor. Okay. So after a certain amount of time, as particles go down the screen, particles will segregate in a way that fine particles will make their way down through the coarse particles, and eventually they will be presented to the screen surface and they pass through. And towards the end of the screen, only coarse particles are left, because you would expect fine particles to pass through, and coarse particles will all roll over and report to the oversize. So obviously, when you operate your screen, you need to target different aspects and you need to maximize different zones. For example, when you look at zone 1 here, or region 1, it is mainly composed of coarse particles. So essentially, no screening is actually happening here. Why? When we say screening, we're talking about fines reporting to the fine portion, coarse particles reporting to the coarse. Here, no fine particle is passing through the screen. So there is no screening happening here. Again, here in region 3, no screening is happening because particles are very crowded and fine particles are trapped within large particles and particles are not falling through. So where actual screening is happening is in this region here, region 2. So what do we need to do? We need to maximize the operation of region 2 or zone of screening, so that we have particles that are fine making their way and screened out. So basically this one here, this slide here is talking about the differences in those 3 regions. The fact that in the last one, it is basically insufficient particles, only coarse are left and no screening is happening. Region 2 is where screening actually happens, and region 1 is insufficient segregation region. So that's what that's talking about. You can read that one maybe on your own time. So as I said, in general, if I want to maximize my screening operation, I would like to maximize region 2. Okay, and that can be done, for example. Okay, so region 2 can be maximized by, for example, decreasing slope of the screen. Okay, so when I say decreasing, particles will spend more time on the screen, and instead of if everything moves quickly, I reach to this point very quickly. So if I move the particle slowly, then I will give it chance for region 2 to be created, and therefore that will help with maximizing your screening efficiency. And also another factor is don't overload the screen too much. Yes, by feeding a lot of material, you increase capacity, but as I said here, if everything is very crowded and this region is really long on the screen, again, nothing happens in this region and your screening performance will suffer. Okay, the last point is moisture. So when we do when I say moisture here and how moisture affects screening, if it's a completely dry material, usually screening is okay. If I'm also doing wet screening, again, screening is not a challenge. But when you have a small amount of moisture there, maybe 1% moisture, that's when you actually have a problem. So it's not dry or wet. It is a material with some amount of moisture in it, and that actually creates a problem. And the problem usually is related to blinding. Okay, so if this was, for example, your screen, so there's one wire here, one wire here, one wire here, and so on. If there's a bit of moisture in the sample, what happens is fine particles start sticking on the wire. And over time, the fine particles will build, and eventually they will block this opening here. Okay, build and block this opening here. So you have a large proportion of blinding of the screens happening. If that's the case, then we call that plastic blinding. Or the other cause or problem is if I have, again, small amount of moisture, fine particles will start sticking together. And eventually these particles will make a lump, a very large lump like this one. And as this goes to the screen, again, it blocks the screen. And that's called blanket blinding. So either you have plastic or blanket blinding happening on the screen, blocks quickly, and that becomes a problem. So you need to use mechanism. Either you need to make sure that the particles are dry before you feed your screen, or you can use other mechanisms to avoid this kind of blinding. So for example, one of the mechanisms we use for avoiding blockage of a screen due to moisture is heating the surface of the screen. Okay, so if I hit the wire here gently, then you prevent this from happening. Okay, so that can be an advantage, okay, to control plastic blinding. So obviously, if I just hit the wire, this can still happen. Okay, before I start screening, this can still blind this the screen, but at least you can prevent the plastic blinding if you hit the screen surface, or you can use mechanical means. For example, we use ball trays that are lifted up and they hit the screen from the bottom. As they hit the screen from the bottom, they actually disrupt some of the blinding happening on the screen. And again, that can be used to reduce blinding. So obviously these are extra operations which can cost you more money. So you might as well just do either simply completely wet screening, or you can just do dry screening eventually to maximize your screening efficiency. Okay, so I have a few slides to go through, but I'll probably pause a little bit and see if you guys have questions. Any questions, guys? So maybe whatever I said answers some of your questions earlier as well, to do with how you operate a screen to maximize efficiency and so on. But any questions? Okay, no questions. Is there a question? Yep.
Okay, I have a question regarding. First, could you show me the surface screening slide?
Yeah. Surface. Which slide? Sorry.
Pyro.
I don't know if I can't hear you much. I don't know which ones you are after.
In Pyro 18 surface screening.
Oh, okay, screening surface. Yep. This one?
No, based on the screening, the surface of the screen.
Oh, okay, yeah, from the back. Okay, yeah. Okay, I talked about this ones here.
My question is, Pyro 18, I would like.
On
polyurethane.
Polyurethane? Yeah.
Yes. There is a advantage and advantages of
Yep.
that. The advantages of the pyroethane,
Yeah.
where the screen is the pyroethane.
Yeah.
It reduces the blinding and noise levels.
Yeah.
Even though it decreases the blinding of the screen,
Yeah.
How can we optimize to get the required liberation in terms of creating?
Yeah.
And,
So
and another question: how can you determine the specific elastic range of the surface area?
specific. Sorry, I don't know what you are asking. Specific elasticity rate.
Yes.
Okay. So here, what we're trying to say is, okay, let's compare maybe something that's made from a metal and something that's made from polyurethane. Okay. So if something is made from metal, it's very rigid. Especially, let's say maybe something is made from a thick woven wire. Okay. So if a particle goes there and blocks it, so that will be stuck there. There's no mechanism of removing it easily. So basically, if you have too many openings that are blocked like that, what happens is your screening efficiency and your screening capacity will suffer very significantly. But when it comes to something that is elastic, let's say in this case the polyurethane, if something goes in the opening and it was momentarily stuck there, because it is elastic, and we also have vibration screen, for example, made from polyurethane, because you have motion applied to it, and because particles are also falling on it constantly, usually what happens is that stuck particle will pass through, will be forced to pass through, because the rubber, or in this case, the polyurethane, is very flexible. So it stretches. When it stretches, particle will pass through. So that's why we say it has lower blinding ability. So it doesn't blind very quickly. So it doesn't block very quickly. Even if something was blocking it, particles can pass through. Okay. So obviously, in the same time, you don't want your screening to be affected if everything is too elastic. Okay. So if polyurethane stress is too much, you are allowing coarse particles to pass through as well. So that can be an issue. But in this case, the polyurethane is very accurate enough, because when you put the holes on the polyurethane, you can cut them very accurately, and it is not very elastic to ruin your coarse particles to pass through, but it is elastic enough to prevent blinding or blockage. So it's actually a hard material. So it's not that easy to stretch it very easily. So it's not like I don't know how I express it. It's not a stretchy material to start with, but it gives you both the advantage of being able to reduce the blinding, but also it gives you the advantage of accurate screening as well. Okay, so you're not compromising the screening by putting a very stretchy material here. Okay, its nature is that is not very stretchy, so you can actually make accurate holes on the polyurethane, but also it's not very rigid like a wire or something like that, which also helps you with reducing blinding. But in terms of a number, I don't know what elasticity factor is for it, but I can check. If you're interested, I can check how elastic or inelastic it is. Okay, if you are looking for a number, but I don't know if there is any actually available in terms of its elasticity factor. Okay, but that's the concept behind polyurethane and their use as a screening surface.
Okay, another question.
Yeah.
Regarding there are a number of factors that will affect our screen device.
Yeah. Yeah.
You are mentioned factors already.
Yeah.
So how can we optimize those factors to get target vibration size?
Okay, so I think what will be good is to look each of them maybe individually. Okay, so as I said here, so for example, for the case of relative size of particle to aperture. So as I said, if I am going to select a particular screen for my operation, the first thing you obviously work out is the capacity of the screen or all that, and that's more dependent on equipment specification. From operational point of view, when I want to pick a particular size for screening, let's say 100 micron, when I say, okay, I want to use 100 micron for my screening operation, so in this case, I'm removing coarse and fine than 100 micron, I need to first look at my feed. I need to look at my feed composition in terms of particle size, and I need to know how the particles are distributed. Okay, I need to avoid if, for example, 60% of my particles are very close to 100 micron, I shouldn't pick 100 micron as a separation size. Okay, so that's why you need to first work out your particle size distribution and determine the size where you're going to conduct your screening operation. The other factor you need to look into is what is more critical for me. Is it capacity or efficiency? And as I said here, whether you decide with efficiency or capacity is actually to do with what you are actually doing the screening for. Okay, it could be for a specific operation that requires accurate screening. In that case, you are telling me that efficiency is more important. If efficiency is more important, then what I need to do is, first of all, you need to have that accurate aperture. Okay, so the aperture is very critical. But the shape of the aperture will be determined by the shape of the particles I'm screening. If I'm looking at elongated particles mainly in my feed, probably I should go with rectangular shape, screen aperture. Okay. If my particles are round, some minerals are actually naturally round. Okay. So the shape is already predetermined. Then you probably can think of more round openings on the screen surface. Again, if capacity is more important, then I'll be looking at, okay, I just want to have as much open area as possible on the screen, and I want to move the screen quickly. Things like that will help maximize the capacity. So again, you need to think of what is the trade-off. If you give me what is more critical, I can always, optimize the screening operation based on that requirement. But always it comes down to why we're doing the screening for. And obviously, as I mentioned, which one is more important? Is it efficiency? Is it capacity? Is it accurate screening, or I'm just happy with rough screening? Okay, so those are important considerations. But regardless, when you operate a screen, these are some of the things you need to look at, okay? So what is my particle size distribution? How close are particles to the aperture? How do I shake the screen? How is the inclination? Things like that are some of the things you need to consider. So what I'm trying to maybe discuss today is more on what are you going to look into when you are operating a screen, rather than giving you this is the best way of operating it, because there is no best way of operating a screen. It all depends on what is the purpose of the screening operation. Okay.
So we are interested in both the change and capacity of the screen.
Yes.
Optimization sense.
So are you?
Both
Yeah.
of the screen as well as the capacity. Regarding that, how can you determine the working conditions of the screen? My question is.
I only am hearing you part of what you are saying.
For example, envelope inflation, one of the factors that we must take.
Yeah.
Our efficiency of bond inflation as well as capacity of screen.
Yeah. እስቲ ወደፊት ናና ጠይቀኝ። ግማሹን ነው ካፓሲቲ ስትል ነው የምሰማህ እንጂ ፉል አልሰማህም የምትለውን
ማለት ያው ጥያቄ ማለት ነው።
እሺ
አሁን እነዚህ የተዘረዘሩት እንትኖች አሉ፣ ሊስት ኦልሬዲ ሊስት የሆኑ ፋክተሮች አሉ።
እሺ
እና የሚፈለገውን ኢፊሽንሲ እና ካፓሲቲ ለማምጣት እንዴት ነው እነዚህን አድጀስት ማድረግ የምንችለው? ኦፕቲማል ፖይንቱ ምክንያቱም ከኦፕቲማሙ ከወረደን ካነሰም ከበዛም ኢንክሪዝ ካደረግነው ከጀመረው ኢፊሽንሲያችንን ካፓሲቲያችንን የሚፈልገውን ላናገኝ እንችላለን። ለምሳሌ አንግል ኦፍ ኢንክሊኔሽን ወርኪንግ አንግል እሱን እንዴት ነው የምናውቀው?
ኦኬ ቬሪ ጉድ። ስለዚህ አንዱን ፖይንት አንስተን ለምሳሌ አንግል ኦፍ ኢንክሊኔሽን እንዴት ኦፕቲማይዝ እናረጋለን ብለን ከሆነ የምንጠይቀው ለምሳሌ 15 ዲግሪ ነው the best angle of inclination ልንል አንችልም ለምሳሌ ማለት ነው። ወይም ደግሞ 20% inclination ቢሆን that's the best ልንል አንችልም። ለምን? አንግል ኦፍ ኢንክሊኔሽንን ስናነሳ የምናነሳው አብረን ምንድን ነው ፓርቲክሎቹ ከላይ ፊድ ሲደረጉ አንግሉ በጣም ሃይ ከሆነ ስቲፕ ከሆነ ቶሎ ይወርዳሉ ፓርቲክሎቹ። አንግሉን ደግሞ ፍላት ካረግ ነው ቀስ እያሉ ነው ፓርቲክሎቹ የሚሄዱት። ስለዚህ እዚህ ጋር ሁለት ነገር ኮምፕሮማይዝ አሁን ፐርፌክቱ 25 ዲግሪ ነው ልንል አንችልም ማለት ነው። ወይም ደግሞ 40 ዲግሪ ነው ልንል አንችልም። ምክንያቱም ለአንዱ ኦፕሬሽን 40 ዲግሪ ፐርፌክት ሊሆን ይችላል። ምክንያቱም የሚፈልጉት ምንድነው ፓርቲክሎቹ ቶሎ ስክሪኑ ላይ ደርሰው ቶሎ እንዲወርዱ ነው የሚፈልጉት። ስለዚህ ካፓሲቲ ነው እነሱ ቶሎ ቶሎ ረን አድርገው ስክሪኒንጋቸውን መጨረስ ነው የሚፈልጉት። አንዳንዶቹ ደግሞ ፓርቲክሎቹ ቆይተው ሰርፌሱ ላይ ቀስ ብለው እንዲሄዱ ይፈልጋሉ። ስለዚህ 15 ዲግሪ ኦፕቲመም ሊሆን ይችላል ለነሱ። ምክንያቱም ሌስ ስቴፕ ባደረግነው ቁጥር አንግሉን ባሳነስነው ቁጥር ምንድነው የሚሆነው ፓርቲክሎቹ ቀስ እያሉ ነው የሚወርዱት። ምን እያደረግን ነው ማለት ነው ኦፖርቹኒቲ እየሰጠናቸው ነው እንዲወርዱ ቀስ ብለው በስክሪኑ ኦፕኒንግ ውስጥ። ስለዚህ እዚህ ጋር አንድ ነምበር ማልሰጥ ኦኬ this is the best operation ማልለው ለምንድን ነው ኦፕሬሽኑ መጀመሪያ የሚፈልገው ምንድን ነው የሚለው መታወቅ አለበት እንጂ ካፓሲቲንም ኤፊሺየንሲንም ባንዴ ማክሲማይዝ ማድረግ አንችልም። መጀመሪያም የጠቀስኩት ለዛ ነው ኮምፕሮማይዝ የግድ መደረግ አለበት። ስለዚህ አንድ ስፔሲፊክ የሆነ ኦፕሬሽን ለምሳሌ የኔ ካምፓኒ ከሆነ ፓርቲክሎቼ እንደዚህ ናቸው የምፈልገው ካፓሲቲ በዚህ መጠን እንዲሄድ ነው ግን ሚኒመም ኤፊሺየንሲ ይሄ እንዲሆን ፈልጋለሁ ካልኩ አንግል ኦፍ ኢንክሊኔሽን የሚወሰነው በዛ ሴት ባረኩት ሪኳየርመንት ነው ማለት ነው። ስለዚህ ሜቢ ለኔ የሚሰራው 25 ዲግሪ ሊሆን ይችላል። ይሄን የምናውቀው እንዴት ነው? በትራያል ኤንድ ኢረር ነው መሞከር አለብን። ምክንያቱም የኔ ፓርቲክል የኔ ማቴሪያል ጎረቤት ካለው ጋር አንድ ላይሆን ይችላል፣ አንድም አይሆንም በብዙ መልኩ። ምክንያቱም ፓርቲክል ሳይዝ አለ፣ አንዳንዶቹ የፓርቲክል ሼፖች ይወስናቸዋል፣ ብዙ ነገር ይወስናቸዋል። ለኔ ስፔሲፊክ ኦፕሬሽን ኦፕቲመም ነው የምለው እኔ ፕሮሰስ ከማደርገው ነገር ጋር የተያያዘ ነው። የኔ ኦፕቲመም ኦፕሬሽን ጎረቤት ላለው ሰው ኦፕቲመም ሊሆን አይችልም በተአምር። ስለዚህ ለዛ ነው እዚህ ጋር አንድ ወጥ የሆነ this is the best operating scenario ወይ ደግሞ ኦፕቲመም የሚሆነው ኢንክሊኔሽን እንደዚህ ሲሆን ነው፣ ስክሪን አፓርቸር ሳይዙ እንደዚህ ሲሆን ነው ልንል የማንችልበት ምክንያት ለምንድን ነው? ከአንዱ ቦታ ከአንዱ ኦፕሬሽን ማሲቭ የሆነ ዲፍረንስ ነው ያለው። ሪኳየርመንታችንም እንደዛው የተወሰነ ስለሆነ ነው ማለት ነው። ስለዚህ የሚጠቅመው ምንድን ነው? በዚህ ዲስከሽናችን ውስጥ ስክሪን ስናደርግ ምንድን ነው አፌክት ሊያደርግ የሚለው ፐርፎርማንስን፣ ምንድን ነው አፌክት የሚያደርገው ካፓሲቲን የሚለውን ካወቅን ወደኛ ኦፕሬሽን ስንመጣ ስፔሲፊካሊ እያንዳንዱን ነገር እየሞከርን ኦፕቲመም የሆነውን እናወጣለን ማለት ነው። እና ብዙ ጊዜ ኦፕሬሽኖች እያንዳንዱ ማይኒንግ ኦፕሬሽን የራሱን ቴስት ነው የሚያደርገው። ኢቭን የራሴን ቴስት አድርጌ ዛሬ ኦፕቲመም ነው ያልኩት የዛሬ ወር ኦፕቲመም ላይሆን ይችላል። ለምን? የፊድ ኮምፖዚሽኑ ይለያያል፣ ሪኳየርመንቱ ይለያያል እየሄደ ባለ ቁጥር። ስለዚህ አንግል ኦፍ ኢንክሊኔሽንን ልጨምረው ልቀንሰው እችላለሁ። ሌሎች ነገሮችን ሙቭመንቱን ልቀንሰው እችላለሁ። ስለዚህ የሆነ አንድ ይሄ ነው ቤስት ኦፕሬቲንግ ሴናሪዮ የሚባል ነገር የለም። ኢቭን በአንድ ኦፕሬሽን ውስጥ ራሱ የሚለያይ ነገር ስላለው ማለት ነው። ኦኬ አይ ሆፕ ሜቢ ማውራው ነገር ጀነራል ከሆነብህ እንደዛ ስለሆነ ነው እንጂ ምንም መጽሐፍ ብታነብ ምንም ኢንፎርሜሽን ብትፈልግ ይሄ ነው ቤስት ስክሪኒንግ ኦፕሬሽን ሊባል የሚችል ነገር የለም ነው የምልህ። I hope it makes sense. ያ ስለዚህ ቁጥርም ስሰጥ እዚህ ጋር ሜቢ አንዳንዱን ሬንጅ አይታችሁ ሊሆን ይችላል። ለምሳሌ እዚህ ጋር ኦፕን ኤሪያ ከዚህ እንደዚህ ሊሆን ይችላል፣ እንደዚህ ኤሪያው እንደዚህ ሊሰፋ ይችላል። አንዳንድ ቁጥሮች አሉ፣ ግን ይሄ ዲፔንደንት ኦን ጀነራል ጋይድላይን ነው እንጂ ስፔሲፊክ የሆነ ነገር ስለሌለው ነው ብዙም ትኩረት ያላረኩትም እዛ ላይ። ለምሳሌ እዚህ ጋር ስለ ስክሪን ሌንግዝ ቱ ዊድዝ ነው የሚያወራው። 2 to 3 ነው ዩዥዋሊ ሌንግዙ፣ ከዊድዙ 2 to 3 ይበልጣል ይላል። ግን አንተ የምትገዛው ስክሪን ስኩዌር ሊሆን ይችላል፣ ሌንግዙ እና ዊድዙ እኩል ሊሆን ይችላል። ያ ማለት መጥፎ ስክሪን ነው ማለት ሳይሆን ለኦፕሬሽን suitable ነው ማለት ነው። ኦኬ ስለዚህ በዛ መልኩ ያዙት ዲስከሽኑ። ኦኬ ሌላ ጥያቄ አለ? ኦኬ ለምሳሌ ትናንትናና ከትናንት ላይ የሄድኩበት ሳይት የሬር እርዝ ሚነራል ፕሮሰሲንግ ሳይት ነው እና ሜቢ ሰሞኑን አሁን ስለ ኮምቢኔሽን ሳወራችሁ 3 አይነት ስቴጅ ኦፍ ክራሽንግ ሊኖር ይችላል፣ 2-3 ስቴጅ ኦፍ ግራይንዲንግ ሊኖር ይችላል። ዲፔንድስ ኦን ሚነራሎጂ እና ስለምንሰራው ነገር ይወስናል እያልኳችሁ ነበር። ለምሳሌ እና የሄድንበት ሳይት አሁን ኮምቢኔሽናቸው አንድ ግራይንዲንግ ቦል ሚል ብቻ ነው ያላቸው፣ ክራሽንግ የላቸውም፣ ሌላ ኦፕሬሽን የላቸውም። አንድ ግራይንዲንግ ሚል ነው ያላቸው። ለምን? እነሱ ማይን ሲያደርጉ ኦልሬዲ ክሌይ ማቴሪያል ነው ሲጀመር ራሱ በጣም አንዴ ማይን ካደረጉት ፓርቲክል ሳይዛቸው ላይክ 5 ሚሊሜትር ምናምን ሆኖ ነው የሚወጣው። ስለዚህ አንድ ቦል ሚል አላቸው፣ በዛ ውስጥ ያሳልፉታል። ዳስ ኮምቢኔሽን ሰርኪዩት ለነሱ ማለት ነው። ስለዚህ አሁን ኦፕቲመም ኮምቢኔሽን ሰርኪዩት እንደዚህ ነው፣ 2 ስቴጅ ኦፍ ክራሽንግ እና 1 ስቴጅ ኦፍ ግራይንዲንግ ያለ ነው ሊባል አይችልም። ለምን? ያ የሚወሰነው በምንድን ነው? ባለን የሚነራሎጂ አይነትና ምን እንፈልጋለን። ኦኬ አንድ ግራይንድ ካደረግነው በኋላ ምንድነው ቀጥለን የምናደርገው የሚለው ነገር ነው የሚወስነው ማለት ነው። ስለዚህ ያ ይሄ እንደዚህ አይነት ዲስከሽኖች ብዙ ጊዜ ብሮድ የሚሆኑት ለምንድን ነው? ሚነራል ፕሮሰሲንግ ስፔሲፊካሊ አሁን ኮምቢኔሽን፣ ስክሪኒንግ፣ ክላሲፊኬሽን በጣም ሳይት ስፔሲፊክ ስለሆነ ነው። አንዱ ሳይት ጋር የሚደረገው ሌላ ነው፣ አንዱ ሳይት ጋር የሚደረገው ኮምፕሊትሊ የተለየ ነገር ነው። ኦኬ
ማለት እሱ ላይ ጥያቄ ማለት ነው።
እሺ እሺ
እሱ ላይ ማለት ስፔሲፊክ የሆነ ሬንጅ የሚፈልገው ምንድን ነው? አሁን ፍሎሺት ልትችል ማለት ነው። ብዙ ጊዜ ሳይዝ እያንዳንዱ የተለያዩ ቨርቲካል ስክሪን ቢኖራው በፍሎሺት ሳይዙ አብሮ ይችላል እና እያንዳንዱ ነገር ኳንታቲ ሊያስፈልግ ይችላል። ከዛ አንፃር አይሰማማ?
የተወሰነውን ፓርት እየሰማሁ ነው፣ ግን ጥያቄ ምንድን ነው አልገባኝም። ስለዚህ አንዱን ፋክተር አውጥተን ኦፕቲመሙ ይሄ ነው ደግሞ ለዚህኛው ፋክተር ኦፕቲመሙ እንደዚህ ነው ብለን ሬንጅ ማውጣት አለብን ነው የምትለኝ? እነዛ ነው እያልከኝ ያለው?
አሁን ፍሎሺት ማለት ነው። አሁን ዲዛይን ላይ ማለት ነው ስፔሲፊክ የሆነ ኳንታቲቭ እያንዳንዱ እንትን ፕሮሰሲንግ ዩኒት ማለት ነው ያስፈልግ ይቀመጣል። ከዛ አንፃር እያንዳንዱ ኦፕሬቲንግ ቫሊዩ ወይም ወርኪንግ አንዱ ለምሳሌ ወርኪንግ አንዱ ለምሳሌ
ኦኬ ያ ገባኝ። አሁን እዛው ጋር ብመለስ አሁን ስለነዚህ ከሆነ የምናወራው ማለት ነው ሪሌቲቭ ፓርቲክል ቱ አፓርቸር ሳይዝ ኦፕቲመም መሆኑን ዲተርሚን የምታደርገው እንዴት ነው? ከርቭ ነው የምትሰራለት። ገብቶሃል? ምን እዚህ ጋር ለምሳሌ ይሄ ከርቭ የሚያሳየኝ ምንድን ነው? ምን ያህል ለኔ ኦፕሬሽን ነው። አሁን እዚህ ጋር ሁሉም ኦፕሬሽን እንደዚህ አይነት ፓርቲክል ሳይዝ ዲስትሪቢዩሽን አይኖረውም። Yeah, I don't know. I hope I understood. ምትለኝን ቢገባኝ ደስ ይለኛል እንድመልስልህ። ስለዚህ የሚሻለው ምንድን ነው? እስቲ እንግዲህ ስፔሲፊክ ጥያቄ ሜቢ እኔ እናንተ መጠያየቅ እንችላለን ወይ በኢሜል ላክልኝ ወይ ደግሞ እዛ እንትን ላይ ቴሌግራም ላይ ሼር አድርግና ሜቢ ዲስከስ ማድረግ እንችላለን። አይ ቲንክ የሆነ ስፔሲፊክ የሆነ ጥያቄ ያለህ ይመስለኛል። ሜቢ ራይት ጽፈህ ብትልክልኝ ሜቢ አንደርስታንድ አድርጌ ይሆናል ምናልባት። ያ ኦኬ Okay. So let's continue our discussion on particle settling. So probably when I talk about this one, I am maybe a bit preempting into classification because most of this is applied to classification, which I'm going to discuss next week. So I wanted to just raise these points here to just prepare ourselves to the next lecture. So as I mentioned, classification is more applied to smaller particles because as I say, if particles are say below 250 micron, usually screening is not as efficient and we typically use classifiers. And the reason for that is classifiers usually tend to use some kind of media and usually they're operated in water. So particles are suspended in water and therefore particles that are finer than 250 micron, they can easily move in water and therefore the separation can be maximized. If you're just using a screen and particles are really fine, what eventually happens is they just lump together and they actually don't segregate from each other very well. So classification is applied when it comes to particles that are smaller than what is normally done for screening. And as I say, these could be particles below, say, 250 micron. But this is just a rough guide again. We can use classification for 1 millimeter particle, 500 micron particle, but generally smaller particles are more applied when it comes to classification. And what does it depend on? Mainly, we explore differences in size. Okay, so we have coarse particles, fine particles. We want to separate them from one another. and basically classifiers can be used for that. The shape of particles and the density of particles can play a critical role, and that actually comes down to what type of classifier you're using as well. Okay, sometimes dense particles can act the same way as coarse particles. If you spin particles in water, if there's some motion applied, particles will attain centrifugal force. Usually the dense particles will start to attain centrifugal force, just like coarse particles. And therefore, small dense particles can go with coarse large particles, okay, depending on the density. So that can be very critical. Shape can again be critical. Flat particles float easily on water, for example, and they can be carried easily with water, even if they're coarse, large particles. If they're flat, they can be easily removed to the overflow, and again, they can respond to the wrong portion. So in classifiers, although we mainly exploit differences in particle size, we can also sometimes use differences in density and so on to result in separation. So you have a feed, okay? Hopefully the feed has coarse and fine particles, and that is split into fine particles because fine particles are slow settling. If you're using a typical classifier like a cyclone, they report overflow. And fast settling particles are those that are large, or maybe they are oversized. And therefore, by using a classifier, the idea will be to separate particles into large and small, or fast settling and slow settling. And that depends whether the particle is fast settling or not, depends on its size, its density, and so on. Okay. So classification can be applied in many cases. So in the flow sheet I showed you earlier, for example, it's used in closed circuit with a grinding mill. So in that case, coarse particles are recycled back to the mill using a cyclone, which is a classifier. Fine particles are sent to the subsequent processing stage. So can be used to control grinding, but maybe we just want to split particles into fine and coarse simply. And coarse is sent to one processing regime, maybe fines are sent into another one. So what you can do is put a cyclone next to a mill, split them into two, okay, without the need for regrinding. You can just split and send them into different directions. And for that, you can actually use classifiers. And maybe you have light and dense particles. Again, you can also classify them. And it can be applied for a number of different reasons. So what determines, again, the performance of a classifier or how good your classifier works? It depends on, again, how particles move inside the classifier. So you can make particles to be crowded. If you're feeding, for example, a material which is 70% solids, you already have too many particles in that feed material. And you have particle-particle interaction. Particle-particle interaction can easily affect your separation performance. Okay, so if particles are not 70% solid, but maybe you're feeding only 10% solid, the remaining is water, particles are free to move in the separator. So in this case, by varying operational factors, you can actually either make it difficult for the particles to move inside the equipment or make it less difficult. And that depends on a number of factors. For example, if you're looking at settling velocity, you're just measuring how fast particles are settling. Okay, so velocity at which particles settle from a suspension. And that velocity will depend on a number of factors. For example, how easy it is for the particles to pass through. If you're measuring terminal velocity is attained when a particle passes through a classifier or a separator, falls from the top, obviously under the influence of gravity. Gravitational acceleration pulls the particles down, but you have buoyancy pulling them up, okay, and fluid resistance pulling them up. So the upward and the downward forces at some stage will come to an equilibrium. When that equilibrium is attained, that particle starts to fall in a uniform rate. And that's what we say terminal velocity is now obtained or attained. Okay. If I have a viscous medium, for example, instead of water, you can use dense media, okay, for separating particles. If that medium is too viscous, again, you're making particles difficult to move, and viscous resistance may be prominent in a typical equipment, or maybe it's actually turbulence. When particles moves in a liquid, it displaces a liquid, okay, moves inside a liquid, and that may also present resistance to flow. So you could have either viscous resistance, mainly because of fluid viscosity, or turbulence resistance, that's mainly due to displacement of the fluid around the particle. And again, these forces will play a role when you're trying to split particles into coarse and fine, or into heavy and light. Okay, so generally, if the resistance is high, your particle acceleration is reduced, and the terminal velocity will be attained very quickly. Okay. In case of free settling, so when I say free settling, we're looking at a situation where the particles are less than 50%. Okay, so the majority of the pulp is made from water, and therefore, if I have a situation where the percent solid is less than 15%, particles are free to move, there is no crowding, okay, and therefore you could say that the Stokes law and the Newton's law can be obtained using those two equations there. And in this case, the Stokes law mainly assumes drag force is predominant. The terminal velocity is given by that expression there. Okay, so G is force of acceleration, D is particle size, and this symbol here is for density of the particles or the solid, and this is for density of the fluid. If it's water, then you know the density of water, and of course viscosity. Okay, so the drag force can be as a result of turbulence resistance. If that's the case, then Newton's law applies. And again, terminal velocity depends on size and density of the particles as well. Okay, so what you're trying to infer from these two expressions is how fast particles settle will depend on either the size of the particle or the density of the particle. So if I'm only dealing with one type of particle, the density is the same. What matters is only their size. If I have different types of particles, maybe one is made from quartz, the other one is made from pyrite, so they have different densities, okay? In that case, density will play a role in affecting the terminal velocity, okay? So if you then simplify those expressions further, so maybe in this case, the classifier uses water as a medium. So density of fluid is known and the viscosity is known. Okay, I know the viscosity of water, I know density of water. So basically these are numbers. Okay, and I know gravitational acceleration. So what I'm saying then is, according to Stokes' law, the terminal velocity is simply a factor of the density of the solids and that of the particle size. And the same applies for Newton's law. If I know density of the fluid, gravitational acceleration is known, so that expression can be simplified here. Okay, so basically in this case, it says in both Stokes' law and Newton's law, terminal velocity depends on size. In this case, if particle size is large, terminal velocity is large. Okay, so particles settle faster. The same is true in Newton's law, when particles are large, terminal velocity large, they settle faster. The other factor is density. If particles are denser, terminal velocity is high. Okay, again, in this case, density becomes critical. So in any case, in both laws, the terminal velocity will depend either on the size of the particles or the density of the particles. But over the years, people have been trying to work and validate these expressions, and it's found that Stokes law applies usually for particles that are smaller than 50 microns, and Newton's law applies for particles that are coarser than 0.5 centimeters. But unfortunately, most of our mineral processing operations work in between those sizes. Usually we work on particles that are around 100 micron, 200 microns, 300 micron, and usually there is a big discrepancy between what we see predicted by these theories and what we actually observe in reality. Okay, but still we use these models to try to predict terminal velocity and try to predict separation performance in a given classifier. Okay, so again, based on those expressions, for example, if particles have the same density, larger particles have a higher terminal velocity and they fall faster. If they have the same size, particles that are denser obviously will have higher terminal velocity and they settle faster. Okay, so it's either the density or the size that matters most. But in reality, what we have is a mixture of particles made from different materials. If you ground a fresh ore, you could have different minerals composing that ore. So you could have different sulfide minerals, you could have silicates, you could have clay minerals. All of them have different densities. And what you're trying to do usually is trying to split particles based on size only. So the density is variable. You're trying to separate them based on size. Okay. And therefore that can present in challenges. So people usually work out what is actually the ratio of sizes between my one mineral and the other mineral that could actually help me separate them from one another, or between one size and another size that I can effectively separate from. So for any given size, say of quartz, obviously needs to be a sufficient size difference between one quartz particle and another quartz particle to be able to separate them from one another efficiently. And that size can be determined based on what we call free settling ratio. Okay, so in this case, maybe you have particles with two densities and two sizes. And maybe you can assume this is suspended in water, for example, so the density is known. So for the first particle, A, for example, you know the size, dA, and the density. You can then again work out Stokes law for the second particle. Again, you know the size and density. So this is based on these expressions here. Okay, so if I take the ratio of one size to another size, dA and dB, so these are maybe two different minerals with two sizes, I can actually work out a ratio. And based on that ratio, I can predict whether the size difference between those two particles is good enough or big enough or not to separate them from one another. And you can do the same for Newton's law. For two particles of different density and size, you can work out settling ratios. And the settling ratio can give you some insights into possibilities during separation from one another. Maybe this example here will help explain what I'm talking about. So if you have, for example, mixture of galena with specific gravity of about 7.5 and quartz with specific gravity of about 2.7, and let's say both of them are being classified in water, you can work the free settling ratio of those two particles based on these expressions here, if Stokes law applied, for example, for smaller particles, or Newton's law for coarser particles. So what it says is, based on that ratio, the free settling ratio between quartz and galena is about 1.96 based on the density, if I apply Stokes law. So basically for smaller particles, okay? And if I apply Newton's law, the free settling ratio of quartz to galena is about 3.82. So what does that mean? What it means is if I have quartz and galena in one mixture at about 1.96 size difference times the size difference, both particles will start to pretty much fall at the same rate. Now I know galena is denser and quartz is lighter. So if the particles was the same size, okay, I know the galena will sink first. Okay, there's no question about it. Why? Because as you can see here, it's denser. But what I want to know is, now I have, say, 100 micron galena. Would 125 micron quartz sink at the same rate as the 100 micron galena? That's what I want to know. Because in my separator, I have both of them. Okay, and in this case, I know the densities are different, and therefore based on density, here, I'll probably go back. As we said here, either the density or the size is what's critical. So if particles are the same size, the density will play a role. If particles are the same density, then the particle size plays a role. But in this example, if we have different particles, so quartz and galena, they have different densities, so they have different settling rates. But what I want to know is, now I have a particle of galena that's 100 micron. If the quartz 100 micron is already known, the galena will fall first, settle first. But how about if the quartz was 125, 150 micron, and the galena was 100 micron? Which one settles first? Just because the quartz was larger doesn't necessarily mean it settles first, because it's actually lighter. It's lighter. So even if it is coarse, it doesn't mean it settles quicker. So I need to know the size ratios that is optimum, or the size ratios that tells me galena needs to be this size and quartz needs to be this size to be able to separate them from one another. And that's actually obtained using the settling ratio. And it says here, after calculating the settling ratio of 1.96, it says a small particle of galena will settle at the same rate as a particle of quartz that is 1.96 times larger. So in this case, almost 2 times larger. So if I have 100 micron galena, it falls at the same rate as 200 micron quartz. Okay. Although the quartz is double the size of the galena, it doesn't necessarily mean it settles faster. Okay, what I'm saying is, in this case, if I have 100 micron galena, and if I have 150 micron quartz, I know already the galena is going to settle faster, even if it is smaller in size. Okay. How about if I have 100 micron galena and 250 micron quartz? I now know the quartz is the one that's going to settle faster. Okay, so what we're trying to do here is obviously taking into account the effect of density in settling. Okay, how about if I was actually dealing with larger particles? Okay, say I'm dealing with 5 millimeter particles. In that case, most likely, maybe the Newton's law applies. But in that case, actually, the galena and the quartz needs to be about 4 times differences in size between the two for them to fall in the same rate. Again, if the galena was, say, 5 millimeter in size, for quartz to settle in the same rate, it needs to be almost 4 times that size. Okay, so maybe like 5 millimeter of galena and 20 millimeter of quartz have same settling rates. If the quartz is smaller than 20 millimeters, the galena is always going to sink first. Okay, so already this settling ratio is telling me possibilities. So when I already plan my classification, I already know these calculations in mind. I can already predict how well my classifier is going to perform based on the proportion of the particles I have, their size, and the corresponding densities. Okay, so the free settling case is obviously a case where particles are not really overloading the separator. As I mentioned, we're talking about maybe less than 15% solids, but usually we might want to push the separator a bit harder. I want to work at 30% solid, 40% solid, even up to 70% solids. Okay, so when that is the case, then you have what we call a hindered settling condition. So in this case, particle to particle interaction is very high. There's interaction between the particles, and therefore particles don't settle very quickly because particles collide with one another. They prevent one another from settling. Okay, so that's very important. So in this case, instead of say assuming water as a media, you can actually assume the pulp itself as the media in which the particles are suspended. So if you look at the previous example, we're looking at fluid as a medium. Okay, but in hindered settling case, we're actually looking at the pulp as a medium. So instead of fluid density, we're looking at pulp density. In any case, this is a hindered settling condition where particles are overcrowded. There's high density, high pulp viscosity condition, and there's a lot of turbulence. So particles will settle at a lower rate, and we can use a modified Newton's law for this one, where the terminal velocity is dependent on the size and not only the density of the particles, but also the density of the pulp. Okay. Again, we can do the same for hindered settling conditions. Okay. And for hindered settling conditions with two particles of different sizes and different densities, you can, for example, go back to the same example, lead and quartz, as we did earlier. But instead of using water, don't know if you noticed, but here I used 1 for density of water. Now maybe the pulp is not of density of 1, maybe it's 1.5. Okay, gram per centimeter cube. Okay, so in that case, specific gravity is about 1.5. Then you can do the same conditions. So for free settling, I told you Newton's law predicts the ratio of 3.82, but in hindered settling case, it's about 5. So this is actually the impact of crowding the pulp with higher percent solids. And what it's saying is actually when you have a situation of hindered settling condition, particles will move slower, okay, compared to free settling condition. And therefore there will be a lot of differences in terms of the impact of density and size on separation performance. So in this case, in hindered settling condition, particle of galena will fall in the pulp at the same rate as particle of quartz, which is about 5 times more in size. Okay, so when people design classifiers, okay, in case of hindered settling, you want to increase the effect of density, okay, on classifier. So in this case, what we're saying is the particles are uniform in size, but the density is different. So I want to explore that. Maybe if you can look at, say, beach sand deposits. When you go to the beach, you dig a sand, particles are actually very uniform in size, but they're made from different densities because they're different particles of different minerals. You can actually run a higher percent solid hindered settling condition. In that case, you know, the particle size is very comparable. So the main way of exploring separation should be density. And therefore you can maximize that by creating a hindered settling condition. But in case where particles are uniform in density, okay, maybe comparable in density, maybe you're trying to separate a silicate from another silicate. In that case, maybe particles are of different sizes, so size effect can be maximized in case of a free settling classifier. So I will talk about different types of classifiers next week and how we can operate them and some of the factors that affect classifier performance and so on. Okay, so I thought I'll just give you a brief about that this week. So maybe one critical factor in our classifier operation is the so-called fluidized or teetering condition. Obviously, when you're running a hindered settling condition, if pulp density is very high, you are significantly restricting particle motion, and that can actually impact separation very significantly. So you might end up with a situation when particles collide with each other continuously, and instead of particles settling against one another, they remain suspended in the pulp for a very long time, and that can significantly impact on capacity and so on. Okay, so probably one of the main equipment that's used for classifier is a hydrocyclone, and I'll talk about a hydrocyclone and its operation next week, so no stress about it for now. Okay, I think that is it for today. I will probably talk briefly about your assignment and how you can complete it, but before that, anyone with a question? Any question on this one? No question? Okay. So I understand there's a bit of a confusion on the assignment and how to complete it, especially part 1. Okay, so I'll probably share it. Okay, so ኤልያስ ምንድን ነው ዋናው ችግር በአሳይመንቱ ላይ?
አሳይመንት ላይ ዋናው ችግር የሚነራል ፕሮሰሲንግ ካምፓኒ አክቲቭ የሆነ አሁን ኢትዮጵያ ውስጥ የለም። የካንቲታም የሚድሮክም ሁሉም በሴኩሪቲ እና በተለያየ ምክንያት ናቸው ኢንአክቲቭ ናቸው።
ያ ስለዚህ የግድ ከኢትዮጵያ መሆን የለበትም። አይ ቲንክ ኤኒ ሀገር ያለ ፕሮሰሲንግ ፕላንት ፒክ ማድረግ ትችላላችሁ። አይ ቲንክ ብዙ ሪሶርስ አለ ኢንተርኔት ላይ ሼር አደርጋችኋለሁ፣ እንዴት መፈለግ እንደምትችሉ፣ ምን አይነት ኢንፎርሜሽን ማግኘት እንደምትችሉ፣ እንደዚህ አይነት ነገር። ስለዚህ ዋናው ችግር እሱ ነው።
ምናልባት ፕራይሜሪ ዳታ ዘሄደን የምንሰበስብ ከሆነ በጣም አስቸጋሪ ነው። ሰከንደሪ ዳታ ኢንተርኔት ከመጻፍ ምናምን ተጠቅመን ከሆነ መስራት አያስቸግርም።
ስለዚህ አንደኛው ጥያቄ ያው ምን አይነት ፕላንት ነው ሰሌክት ያደረጋችሁት? የጎልድ ፕሮሰሲንግ ፕላንት ነው ወይ የኮፐር ነው? ምንድነው ፕሮሰስ የሚደረገው ነው የመጀመሪያው ፓርት። ስለዚህ ብሪፍሊ ሜንሽን ማድረግ ትችላላችሁ እሱን። ብዙዎቹ ኦፍ ኮርስ አንዳንዶቹ ፍሎሺታቸውን ለፐብሊክ አያወጡም፣ ግን ደግሞ በዛው መጠን ደግሞ ፐብሊክ ላይ ሪሊዝ ያደረጉ ደግሞ ብዙ አሉ። አሁን የኮምቢኔሽን ሰርኪዩታቸውን ክራሽንግ፣ ግራይንዲንግ፣ ሚል ምን አይነት እንደሚጠቀሙ ምናምን እንደዚህ የሚያወጡ አሉ ፐብሊክ ኢንተርኔት ላይ ፍሪሊ አቬይላብል የሆነ ማለት ነው። ስለዚህ እነሱን ፒክ አድርጋችሁ ምን አይነት ኮምቢኔሽን ሰርኪዩት ነው የሚጠቀሙት የሚለውን ራፍሊ ስኬች ማድረግ ትችላላችሁ ለሁለተኛው ጥያቄ። ለሶስተኛው ጥያቄ አሁን ሰርኪዩቱን ካገኛችሁ፣ ፍሎሺቱን ካገኛችሁ ሜቢ ክራሸራቸው ጃይራቶሪ ክራሸር ሊሆን ይችላል፣ ሳግ ሚል ሊጠቀሙ ይችላሉ፣ ቦል ሚል ሊጠቀሙ ይችላሉ። ሞር ለምንድን ነው እንደዛ አይነት ነገር የሚጠቀሙት? ጎልድ ፕሮሰሲንግ ፕላንት ነው ካላችሁ ለዛ ጎልድ ፕሮሰሲንግ ፕላንት ለምንድን ነው ያ ኮምቢኔሽን ሰርኪዩት የተመረጠው የሚለውን ዲስከስ እንድታደርጉ ነው አንደኛው ጥያቄ እዛ ላይ የሚያሳየው። ስለዚህ ምናልባት አሁን ለምሳሌ የጎልድ ፕሮሰሲንግ ፕላንት ከሆነና ይሄ ነው ዋናው ሚነራል ኮምፖዚሽን ብለው ሜንሽን የሚያደርጉ ከሆነ ስለዛ ሚነራል ያለውን ሃርድነሱን አንዳንድ ነገሩን ሜንሽን ማድረግ ትችላላችሁ። ከሌላ ሶርስ የግድ እዛ ቦታ መሆን የለበትም። ከሌላ ሶርስ ያንን ፒክ ማድረግ ትችላላችሁ እና ዲስከስ ማድረግ ትችላላችሁ ኢን ዲቴል። ከዛ አራተኛውን ደግሞ ለመመለስ አጌን ጆ ክራሸር ሜንሽን ካደረገ አንዱ ሳይት ሜንሊ የጆ ክራሸር አድቫንቴጅ ምንድነው ዲስአድቫንቴጅ ምንድነው እንደዚህ አይነት ነገሮችን HPGR ከሆነ ሃይ ፕሬሸር ግራይንዲንግ ሮል የሚጠቀሙ ከሆነ ለግራይንዲንግ ለምንድን ነው የተጠቀሙት ያንን አድቫንቴጁ ምንድነው እንደዚህ የሚለውን ዲስከስ ማድረግ ትችላላችሁ አይ ቲንክ በዛ መልኩ ያዙት ከዛ በኋላ ምንድነው ያሰብኩት አይ ቲንክ ለምሳሌ እንዴት ነው የምናገኘው አሁን ኦፕሬት እያደረጉ ያሉ ማይኒንጎችን ለምሳሌ አውስትራሊያ ያለ ካናዳ ያለ ኦር አሜሪካ ያለ እንዴት ነው የምናገኘው ካላችሁ አይ ቲንክ ብዙ መንገድ ሊኖር ይችላል ግን እንደ ኤግዛምፕል ላሳያችሁ ለምሳሌ በእርግጠኝነት ስለ ካናዳ ያሉ የኮፐር ፕሮሰሲንግ ፕላንት ብትሉ ብዙ ኢንተርኔት ላይ ሶርስ ማግኘት ትችላላችሁ ቺሊ ያለ የኮፐር ፕሮሰሲንግ ፕላንት ብዬ ጉግል ባረግ ብዙ ነገር ይወጣልኛል ይሄ ፕላንት ኮፐር ትሪት ያደርጋል የሚል ማለት ነው ከዛ አንዱን ፕላንት ፒክ አድርጋችሁ እዛ ፕላንት ያለውን ኢንፎርሜሽን ፐብሊክሊ አቬይለብል የሆነውን ብትፈልጉ ለምሳሌ ከካናዳ ሄዳችሁ ከካናዳ ሰድበሪ ያለው የኒኬል ፕሮሰሲንግ ሊወጣላችሁ ይችላል ሰድበሪ ስፔሲፊክ ኦፕሬሽን ደግሞ ሄዳችሁ ሞር ኢንፎርሜሽን ስለዛ ማግኘት ትችላላችሁ ፈርዘር አንዱ ላይ የሄዳችሁ ማለት ነው ከዛ በኋላ ሰድበሪ ጋር ማን ነው የሰድበሪ ኦፕሬሽንን ራን የሚያደርገው አሁን ሚድሮክ እንደምንለው አገር ቤት ሰድበሪም ለምሳሌ ግሌንኮር ነው ራን የሚያደርገው ከዛ እነሱ የራሳቸው ዌብሳይት አላቸው ስለዛ ኦፕሬሽን በዝርዝር ያወራሉ እዛ ላይ ኮሚኒኬሽን ሰርኪታችን እንደዚህ ያለው ምናም ብሎ ያወራሉ አንድ ሶርስ እሱ ነው ያንን ኤክስፓንድ እያደረጋችሁ ሜቢ ሌላ ቦታ ደግሞ ፐብሊሽ የተደረገ እዛው ግሌንኮር ላይ እዛው ሳይት ላይ ሌላ ሶርስ ይኖራል እንደዛ እያደረጋችሁ አይ ቲንክ ኤክስፓንድ ማድረግ ትችላላችሁ ያለውን ነገር ማለት ነው እና ለምሳሌ ይሄ እዚህ አውስትራሊያ ያሉ የጎልድ ፕሮሰሲንግ ፕላንቶች ናቸው እነዚህ ዝም ብዬ እዛ ጋር ሼር ያደረኩት ያ ፕሮሰሲንግ ፕላንት ምን አይነት ሪሶርስ አለው ኢንተርኔት ላይ ብዬ ዝም ብዬ ራፍሊ ስፈልግ የወጡት ናቸው እነዚህ ይሄ ብቻ ነው ያለው ማለት ሳይሆን እንደዚህ አይነት ተመሳሳይ የሆኑ ሪሶርሶች አሉት ያንዳንዱ ፕሮሰሲንግ ፕላንት ስለዚህ እንደዛ አርጉ ይሄን ሼር ላርጋችሁ እንደመነሻ ለምሳሌ ከአውስትራሊያ ከካናዳ ከቻይና ከቺሊ ዝም ብዬ ያወጣሁት ሶርስ ነው ከስር ያሉት ሊንኮች ለየዛ ሳይት ዲቴል የሆነ ነገር የሚያወሩ ናቸው እና አንዳንዶቹ ኮምቢኔሽን ሰርኪዩት አላቸው አይ ቲንክ ኦልሞስት ብዙዎቹ እዚህ ጋር ሊንክ ያረኳቸው ለዛ ሳይት ስፔሲፊክ የሆነ ኮምቢኔሽን ሰርኪዩት ሜንሽን ያደርጋሉ ምን አይነት ክራሸር ምን አይነት ሚል እንደሚጠቀሙ ያወራሉ ከዛ ተነስቶ ኤክስፓንድ ማድረግ ይቻላል ያንን ከፈለጋችሁ ማለት ነው ስለዚህ ሆፕፉሊ አገር ቤት ብቻ ሊሚትድ ሳትሆኑ እነዚህን ኢንፎርሜሽኖች ማግኘት የምትችሉ ይመስለኛል ካቃታችሁ ደግሞ ለሚ ነው እና ሞር እኔም ወይ ሪሶርሶቹን ሁሉንም ሼር አደርጋችኋለሁ ከዛ በዛ ሪሶርስ መሰረት ሜቢ አሳይመንታችሁን ኮምፕሊት ማድረግ ትችላላችሁ ሞር የምፈልገው ምንድነው ዝም ብሎ question and answer ነገር ከሆነ is easy ለእናንተ I hope ግን ሞር እንደዚህ አይነት ነገር ብትሰሩ አንደኛ ታነባላችሁ ለምሳሌ ስለ ኦሎምፒክ ዳም ታነባላችሁ እንዴት ነው ፕሮሰስ የሚያደርጉት የሚለውን ታነባላችሁ አንድ ሶርስ ሳይሆን ሌላ 5 6 7 ሪሶርስ ታነባላችሁ በዛ ሳይት ላይ I think ሪሰርች ስታደርጉ ሞር ብዙ ነገር ትለምዳላችሁ ሚል ሐሳብ ስላለኝ ነው በዛ ላይ ደግሞ ስትጽፉት ያነበባችሁትን ነገር ሞር አንደርስታንዲንጋችሁ እየሰፋ ይሄዳልና I don't know ቻሌንጂንግ ሊሆን ይችላል ግን እንደሆነ እንደ ኦፖርቹኒቲም ወሰዱትና አንዳንድ ነገር ለመማር ይጠቅማችኋል
ፎር ኢንዲቪጁዋል ነው
አቤት
ኢንዲቪጁዋል ነው የሚሰራው ወይስ በግሩፕ
ሪፖርቱ መጀመሪያ ያሰብኩት ኢንዲቪጁዋል ነው ግን በግሩፕም መስራት ከፈለጋችሁ ኦኬ ነው ግን ምንድነው እሱ አንድ እንትን ግሩፕ ሪፖርት አለ የላቡ እሱ የግሩፕ ነው ስለዚህ ከአንድ በላይ የግሩፕ አሳይመንት ባይኖር ጥሩ ነው ስለዚህ ለዚህ ነው ይሄ ሞር ለኢንዲቪጁዋል እንድትሰሩ ሁሉም የራሱን ኤፈርት ኮንትሪቢዩት እንዲያደርግ የፈለኩት ለዛ ነው አይ ቲንክ ወርድ ሊሚት ሰጥቻችኋለሁ ብዙ ሰው እንዳይጽፍ ወይ ደግሞ ትንሽ እንዳይጽፍ የሆነ እንደ ጋይድ የሚሆን ነገር ወርድ ሊሚት ሰጥቻችኋለሁ ስለዚህ እሱን ፎሎ አድርጉ ኦኬ ነው አሁን ያ አይ ቲንክ ያው ሁሉም ቦታ ነው የሪሶርስ ችግር ሁሌም ፐብሊክሊ አቬይለብል አይደለም የብዙዎቹ ኢንፎርሜሽን የብዙዎቹ ማይኒንግ ካምፓኒዎች ኢንፎርሜሽን ፐብሊክ ላይ የለም ግን አትሊስት ያሉትን ሞር ኤክስፕሎር ማድረግ ትችላላችሁ አንድ ካገኛችሁ ከዛ ኤክስፓንድ ማድረግ ነው ስለዚህ ሞር የእናንተ የሪሰርች አቢሊቲም ሊወስነው ይችላል ስለዚህ ምን ላድርግ መሰለህ ይሄንን ሼር ላድርግላችሁ ልላክልህ ይሄኛውን ዝም ብሎ ራፍ የሆነ እንደ ኤግዛምፕል ነው እዛው ላይ ደግሞ አንዳንድ ሪሶርሶች ዝም ብዬ ዳውንሎድ ያረኳቸው አሉ እነሱንም ልላክልህና አንተ ሼር አድርግ ከልጆቹ ጋር ከዛ እንደመነሻ ይሆናችኋል እሱ ኦኬ አይሰማኝም ጥያቄ የሆነ እየጠየቃችሁት ያላችሁት አይሰማኝም
ምናልባት ኢንዲቪጁዋል ሲሆን በእርግጥ አሁን የሰከንደሪ ዳታ ከኢንተርኔት ምናምን አውትሶርስ አድርጎ መስራቱ ለእኛም ያስቸግረን ግን ምናልባት አሁን አንዳንዶቹ ተመሳሳይ አሁን አውትሶርስ የምናደርጋቸው ካምፓኒዎች ቢመሳሰሉት
ምንም ችግር የለውም የግድ አንድ አይነት ከሆነች አልቀበልም የሚባል ነገር የለም አንድ ካምፓኒ 10 ሰው ሊሰራበት ይችላል ግን 10ሩም ሰው የራሱ ከሆነ ሪሰርች ያደረገው የራሱን ሶርስ ከሆነ የወሰደው የራሱን ኢንተርፕሪቴሽን ከሆነ ያደረገው በተአምር ሊመሳሰል አይችልም የ10 ሰው ሐሳብ የተለያየ ስለሆነ ማለት ነው ስለዚህ አንደርስታንድ
ለጋራንቲ ይዛል ሳይሆን ምናልባት ሁላችንም በየግላችን የምንፈልገው ምናልባት እኔ የሰራው ካምፓኒ ሌላው ቤት ሆኖ ከሚሰራው ካምፓኒ ጋር ሊመሳሰል
ምንም ችግር የለብኝም እንዳልኩ ነው አሁን 30 ምናምን ናችሁ 7 ሰው አንድ አይነት ካምፓኒ ፒክ ሊያደርግ ይችላል እያልኩ ነው ስለዚህ የራሳችሁ ከሆነ ስራውና የራሳችሁ ሰብሚሽን ከሆነ ተመሳሳይ ካምፓኒ ፒክ ማድረጋችሁ ብቻውን ምንም ችግር የለውም ኦኬ ኦኬ ግልጽ ከሆነ በቃ ልክልሃለሁ ይሄንን ከዛ ዲስከስ ማድረግ እንችላለን የቀረውን ነገር
ግልጽ ነው እናመሰግናለን
ኦኬ እሺ መልካም
ሄሎ ዶክተር
አቤት
ያውኑ ስራው ላይ ትንሽ በግሩፕ
አቤት
እያንዳንዱ ግሩፕ ሜምበር የራሱ ኮንትሪቢዩሽን ያለበት ሆኖ ብንሰራ የበለጠ ኤክስፒሪየንስም ሼር ማድረግ አሪፍ ነበር ላቡ ያለው ኦሬዲ ላብ ቴክኒሻንም ስላለ አንዳንድ ነገር እንትን ያደርገናል የኛውን ትንሽ ስታንዳርዱ አሪፍ ስለሆነ ለምንሰራው ፕሮጀክትም ጠቃሚ ስለሆነ ግሩፑ ባይበዛም የተወሰኑ 2 ወይ 3 ሆነን አንድ እንትኑ ላይ ብንሰራ የበለጠ አንዱ ያላየውን አንዱን እያየ ኢንተርፕሬቴሽን ለመተጋገዝ ጥሩ ነበር ኢንዲቪጁዋል ኮሞን
ስለዚህ የአብዛኛው ሰው ሐሳብ ይሄ ከሆነ ምንም ችግር የለብኝም አትሊስት 5 ሰው በአንድ ግሩፕ አድርገን መሄድ እንችላለን ይሄ ማለት ግን ያው የዩኒቨርሲቲያችሁን ህግ አላቀውም ምንድነው አሁን ለምሳሌ እዚህ ዩኒቨርሲቲ ያለው ህግ ምንድነው ግሩፕ አሳይመንት ከ30% በላይ መሆን አይችልም ላቡንና ይሄንን አንድ ላይ ካረግ ነው ኦልሞስት 50% ግሩፕ ወርክ ሊሆን ነው ማለት ነው ስለዚህ ችግር የለውም የምትሉ ከሆነ በዛ በአዲስ አበባ ዩኒቨርሲቲ ህግ ብዙ የግሩፕ ወርክ ቢበዛም ምንም ኢፌክት የለውም የምትሉ ከሆነ አም ኦፕን ምንም ችግር የለብኝም በተለይ መተጋገዝ የምትችሉ ከሆነና ጥሩ ኳሊቲ የሆነ ስራ ሰሚት ማድረግ እንችላለን በዛ መልኩ የምትሉ ከሆነ አም ኦፕን ስለዚህ የአብዛኛው ሰው ሐሳብ ነው በግሩፕ እንስራ የሚለው
ይሰማል ዶክተር
ይሰማል
በቃ ተስማምተናል የግሩፕ ሁሉም በግሩፕ ይሆን ሳይሆን በቃ ችግር የለውም በሱ እንጨርሳለን ተስማምተናል
በግሩፕ
አይ ኖ በአሁን አሳይመንት
በኢንዲቪጁዋል ኦኬ
ላቡን በግሩፕ ማለት ነው
ላቡ የግሩፕ ኢንዲቪጁዋል አሳይመንት ኦኬ ጥሩ እሺ አይ እንዳልኩት የማጆሪቲው ሐሳብ ያ ከሆነ ምንም ችግር የለብኝም ግን በኢንዲቪጁዋልም አብዛኛው ሰው የሚስማማ ከሆነ ምንም ችግር የለብኝም። ስለዚህ ለአሁን ኢንዲቪጁዋል በሚለው ነው ያዝኩት ማለት ነው።
አሃ
ኦኬ ጥሩ። እሺ
እሺ ዶክተር እሺ
መልካም።
አሳይመንት ከ30% በላይ